Hi class, today we're going to be dividing polynomials, but before we do that we need to add a few of our exponent rules onto our bag of tricks that we have. So far we have already taken a look at two exponent rules. We had the product rule, which was if you had two things with like bases and you were multiplying them, you would add the exponents. We also had a power to a power rule, where if you had something raised to a power, we'll actually put x to the m here, to the n, that you just multiplied the powers. And this could be expanded to where if you had multiple items in here with a power outside, you would just apply that power to everything inside. And that also worked for things that were in fractions. So since you multiply fractions straight across, if you had x to the n over y to the m, you would just, and that was all raised to a p, you would just multiply your exponents and get x to the np and y to the mp, applying that power to everything inside, even if you have a fraction. Now we're going to expand these a little bit to rules that you might need when you're dividing. So let's examine a problem that you might be confronted with. Let's say you had x to the fifth and you were going to divide it by x cubed. If you remember, a fraction bar means divide. Now what we're going to do is we're going to expand this out into what it really means. And x to the fifth is really x times x times x times x times x. And x cubed is really x times x times x. Now if you have something divided by itself, it's really 1. So if you had something like 5 over 5, you would actually simplify it into the number 1. Same thing can happen with x over x. So we can actually pair these up and say, well, these two x's will make 1, these two x's will make 1, and these two x's will make 1. And so they kind of cancel each other out. And notice there's nothing left in the denominator. Well, you always have an invisible 1 being multiplied by any variable. So there's really a 1 in the denominator. But you don't have to write a 1 in the denominator. So really all we're left with is an x times an x, which actually is just x squared. Now let's examine what just happened. We were dividing two things, and x to the fifth is being divided by an x cubed. And we ended up with an x squared. If we don't want to do all of this in order to get to here, we can examine what we had here and see if there's a shortcut. And notice 5 minus 3 is 2. So when you divide and your bases are the same, you can really just subtract the exponent of the variable you're dividing by from the exponent of the variable that you're dividing into. So that would, if it's written as a fraction, be your top exponent minus your bottom exponent. And that makes sense because dividing, you subtract your exponents, and over here when we multiplied, we added the exponents, and division is the opposite of multiplication, and subtraction is the opposite of addition. So let's go ahead and summarize this into a rule here, which we are going to call our quotient rule. And we will use this rule to come up with a couple more rules. And the quotient rule is if you have like bases and you are dividing, all you have to do is subtract your exponents. Now let's expand this a little bit and take a look at, what if I had x squared over x squared? Well, since that is something divided by itself, intuitively we would say, well, that answer is 1. But what if we apply this quotient rule up here? If we apply this quotient rule up here, we need to do 2 minus 2, which gives us x to the 2 minus 2, which is x to the 0. What we've just done algebraically is we've shown that x to the 0 is the same thing as 1. And that is what our zero exponent rule is. But we have to keep something in mind. In order to show this, we had an x squared in the denominator of something, and you can't divide by 0. So you need to make sure that for this rule that your x here is not 0, because that's how this would be 0 here. So when we write our rule for this, we are going to have our 0 exponent rule, that if something's raised to the 0 power, it's 1. That's provided that x is not equal to 0. So that is something that you want to keep in mind. Now that's our second rule. Let's take a look at one more rule that we'll need in order to do division. And on that rule, we're going to look at it kind of in a similar way as what we just did for the 0 exponent rule. Let's say that we have x cubed, and we're dividing it by x to the 5th. Now, if we look at it using this quotient rule here, we would do 3 minus 5. And we would have x to the 3 minus 5, which equals x to the negative 2, which, notice, that's a negative exponent. Now let's look at this problem in a little different manner. So we know that this problem is the same thing as x to the negative 2. But if we look at this problem, x cubed over x to the 5th, the same way that we came up with our quotient rule up here, and we expand it out knowing that x cubed is x times x times x, and that x to the 5th is x times x times x times x times x, what we can do is we can pair up the x's and cancel them. So these x's would cancel, these ones would cancel, and these ones would cancel. Notice that leaves us with 2 of them down here on the bottom. Now, we don't see anything up here on the top, but remember we have an invisible 1 being multiplied by any variable without a coefficient. So really there's a 1 in the top of this fraction. So this is really 1 over x squared. What we've just shown is that this is the same thing as this. Let's examine the difference between these two things. This one here has a negative exponent, this one has a positive exponent. But if you take this one, which really has a 1 in the bottom, and you flip it over, you get this one. So the difference between these two is that they're reciprocals and their exponents have opposite signs. And that's what you do with what we call our negative exponent rule. Often you'll need to write things without negative exponents. And if you're writing something without negative exponents and it has a negative exponent based on this rule, you can take the reciprocal and change the exponent to a positive. So let's go ahead and formalize this rule. It's our negative exponent rule, that if you have something with a negative exponent and you need to make it a positive exponent, you take the reciprocal and change the sign of the exponent. Now, these are all of your rules for exponents here. It will be handy for you to put them all on a 3x5 note card and maybe use that as a bookmark for yourself and keep it next to you while you're doing your problems. That way, if you need to refer to it, you can, and it'll help you as you're studying and practicing your problems to prepare for an exam. So I would put all of these on a 3x5 note card and have them available for you as you're doing your practice problems. Now let's do a problem that uses many of these, maybe not all of them, but many of these rules here that we've learned about. And it's going to also have some division in it because it's going to be written as a fraction. So that will require you to use your quotient rule here, and it'll get us started in our dividing. We're going to start out a little bit easy. We're going to start with 25x squared y cubed divided by 35x y to the fifth. Now, first of all, I notice this x on the bottom here does not have an exponent, so let's insert a 1 just to remind you that it's there. This is actually a monomial divided by a monomial, and we're going to actually be using two rules for this. We're going to be using the negative exponent rule and the quotient rule for this. Now, I'm going to show you a process that actually will help you totally bypass the negative exponent rule, and that is going to make it a little easier for you to deal with your problems. We're going to do this problem by just reducing it as if it was a fraction, and we'll start with the numbers. If you look at 25 and 35, we could reduce that by dividing 5 into both of those. So let's go ahead and do that. 5 into 25 is 5. 5 into 35 is 7. So when we continue on with this problem, we'll have a 5 in the numerator and a 7 in the denominator. Now let's take a look at our x's. We're going to divide these x's, but I want to use the quotient rule and make it so that I don't have any negative exponents. So what you're going to do is subtract your exponents, but leave your variable where there's more of them. And notice on the x's there's more of them in the numerator, so that's where they're going to stay. And you can think of it as this 1x is going to cancel one of these. So this is going to take this away and reduce this from 2 down to 1. And that's going to leave us in our final answer with just an x to the first power, which we just write as x in the numerator of our answer. Now we're going to do a similar thing with the y's. Notice there are more y's down here. This y to the fifth means we have 5 of them multiplied down here, so there's more, and there's only 3 up here. So we're going to think of it as these 3 will cancel with 3 of them down here, which will leave 2 there. That's going to look like these cancel with 3 here, leaving 2 there. Notice they're in the denominator, so when we write them in our answer, I'm going to have a y squared right here. And this is what we end up with for a final simplified expression. Now, that was one that's a little bit easier, and we avoided the negative exponent rule. Let's take a look at one where we can't really avoid the negative exponent rule. Let's say that it's 6x to the negative 3. This one, we can't avoid the negative exponent rule, and it seems fairly simple, but for a lot of people this is a fairly difficult problem. And basically the only rule it's going to use is the negative exponent rule. You can think of this as 6 times x to the negative 3. That negative 3 for your exponent here is only attached to the x because there's no parentheses around your 6 and your x. So think of this as 6 over 1, and this one, in order to make a positive exponent, we're going to take the reciprocal and change the sign of the exponent. That gives us 6 over 1 times 1 over x cubed. If you multiply straight across, you end up with 6 over x cubed. Notice that a shortcut to get from here to here would be to just take this and move it to the denominator. In fact, that's what we're going to do for most of our problems that have negative exponents. If the negative exponent is in the numerator, we're going to move it to the denominator because that's the reciprocal. If it's in the denominator, we're going to move it to the numerator because that's the reciprocal. So let's go ahead and take a look at a problem that has more negative exponents in it. Let's say that we have a to the negative 4, b to the negative 5 over a squared b to the negative 6. Now you want to remember, you only move things with negative exponents. If it has a positive exponent already, you want to leave it where it's at. So we're going to go through this problem, and if something has a negative exponent and it's in the top, we'll move it to the bottom. If it's in the bottom, we'll move it to the top. So let's do one item at a time. If we take a look at this a here, it has a negative 4 for an exponent, and that's negative, and it's in the top, so we're going to move it to the bottom. So this is in the top, it's going to go down here. That leaves us with an a to the 4th down here in our next step. Now, let's take a look at the next thing in the numerator. We have a b with a -5 for an exponent, which is negative for an exponent. So since this is in the top, we'll move it down below. This will move down here, and we're going to also have a b to the +5 down here in the next step. If we take a look at the next item, which is down here, this is an a to the +2. Since that's already positive, we're not going to move it. We're going to leave it right where it's at, and I'm going to put it right here next to its like term that's going to multiply by it. Now let's look at the next item. We have a b with a -6 for an exponent, and we need to change that to a +6. So since it's in the bottom, we're going to move it to the top. So this will go from here up to here, and we have a b to the 6th up here. Now everything has positive exponents, so we can go ahead and simplify. We're going to end up using both the product rule and the quotient rule. So let's start with the product rule, which is used down here to multiply our a's. Product rule means we have to add the 4 and the 2, and we'll get a to the 6th down here. Now the quotient rule, we're going to subtract exponents, and notice that there are more exponents up here, so these 5 will cancel with 5 up here. That's going to look like these, take away 5 here, and leave you 1 up top. Now when you only have an exponent of 1, you don't have to write it. So really all we need in the numerator is just a b, because that's an implied b to the first power. And now there aren't any other rules we can apply, and this is completely simplified. So on a problem like this, you want to take care of your negative exponents first, and after you take care of your negative exponents, then apply your other rules, and that will make it much easier for you. Let's take a look at one more problem that uses all of these rules, and then we'll move on to dividing. So let's take a look at this particular problem. We have 2x to the -2 y cubed over 10x to the -5 y to the -2. And this whole thing is raised to the -4 for an exponent. And actually, I'm going to add one more in here. I'm going to put a z to the 0 right here for just a little extra there for you to think about. Now what we're going to do is take a look at this whole thing. There's a lot going on in here, and we want to figure out where in the world would we even start. Well, order of operations, the location where you start is in the parentheses. And I notice in this parentheses I can do quite a bit. There's a lot of reducing that can happen. I also have negative exponents in here. So I'm going to go ahead and do anything that can be done in here before I ever even go to this exponent on the outside. So let's first of all take a look at these numbers. I can reduce the 2 and the 10. 2 goes into 2 once, and 10 5 times. So when I go to my next step, I'm still going to have parentheses with the -4 out here, and I'm going to have a 5 in the denominator. I will leave a 1 up there, but I might not need to have it. If I have variables up there, I won't need it. Now let's take a look at our x's. If you take a look at our x's, this has a negative exponent, and it's in the top. So let's move it down here. That's going to take this and put an x squared down here. Now let's take a look at the other x. The other x also has a negative exponent, and it's in the bottom, so we're going to move it to the top. So this x to the -5 will go up here and be an x to the +5. And notice we won't need that 1 anymore because there did end up being a variable up in the numerator. So now let's take a look at our y's. This y squared, or y cubed here, has a positive exponent. So we're going to leave it where it's at for right now and not do anything with it. If we look at the other y here, this has a -2 for an exponent, and it's in the bottom. We need it to have a positive exponent, so we're going to move it to the top. So That's going to take this and move it up here, so we will have a y squared up here in the next step. And then finally, let's look at that z. That's a z to the 0. Isn't z to the anything that's non-zero raised to the 0 power 1? So really, this z to the 0 is 1. So 1 times all of this is going to be just all of this. So I don't really need that 1, and the z to the 0 can actually just disappear, which was kind of nice. So let's take a look at what we have left here. There's still more I can do inside this parentheses, because I can divide these x's by subtracting exponents and multiply these y's by adding exponents. Let's start with the x's here. These two x's will take 2 away here, leaving 3. So we'll cancel those with 2 of those and leave 3 there. That's going to leave us in our next step with still having a 5 in the denominator, but we're going to have an x cubed in the numerator. And notice we'll still have that negative 4 outside our parentheses because we haven't done anything with it yet. Now let's multiply our y's, and when you multiply you add the exponents, and 3 plus 2 is 5, so that'll be a y to the 5th. Now if we look at what's inside the parentheses, it's in its simplest form, and there's nothing else we can do. So we'll go to the outside of the parentheses and take care of this exponent. And since it's a negative exponent, we need to get rid of the negative first. And a negative exponent tells you to take the reciprocal. Since we're dealing with a fraction inside the parentheses, we're going to take the reciprocal of the entire fraction, and that will take care of the negative on this exponent and make it a positive. So in the next step, this fraction inside turns into 5 over x cubed y to the 5th, and now we have a positive 4 on the outside. And we can just apply a positive 4 to everything inside. So 5 to the 4th is 5 times 5 times 5 times 5, which is 625. And then x cubed to the 4th, we multiply the exponents to get an x to the 12th. And then y to the 5th to the 4th, we multiply the exponents to get a y to the 20th. And this right here is your final simplified answer for this particular problem. Those are types of problems that you may have to deal with that use your exponent rules and combine multiplication, division, and negative exponents, power to power, all of those rules together. Let's take a look at just some basic dividing. Now, a little bit earlier, we did a basic division problem that's similar to what you see here. Say 24 x to the 6th over 6x squared. And really all we had to do was reduce this like it was a fraction. So we could say 6 goes into 24 4 times. So in our next step we would have a 4 up here. And then we could subtract the exponents here and say these two x's take 2 away here. That leaves 4 in the numerator, and the final answer would just be 4x to the 4th. And that one actually probably looks like a fairly simple problem based on what we just did in the previous problems. Now we're going to apply this to taking and multiplying or dividing a polynomial by a monomial. Now, notice that I wrote this as a fraction here to signify the division, and that's partly because we're going to use fractions when we do this particular type of problem. Let's say that you have 50 x to the 5th plus 20x, oops, I said x to the 5th there, and 20x to the 4th minus 30 x cubed. And let's say you're dividing that by 10 x to the 4th. So this is your particular problem. Now, if that's your particular problem, notice that what you're dividing by is a monomial down here. It's just one term. So when you just have one term that you're dividing by, and you have multiple terms up here in your polynomial, what you want to do is similar to distribution. You're going to actually rewrite this as fractions, one for each item in your polynomial, and all of those will have what you're dividing by as its denominator. So this is going to turn into 50x to the 5th over 10x to the 4th plus 20x to the 4th over 10x to the 4th minus 30x cubed over 10x to the 4th. Now all you have to do is go back and reduce each of those fractions and you'll have your answer. So starting with the first one, 10 goes into 55 times. And these 4x's take 4 away here, leaving 1. So the first term is just a 5x. In the second one, 10 goes into 20 2 times. And notice those x to the 4's cancel. So the second term just turns into 2. And then finally with the last one, 10 goes into 33 times. And notice there are more of the x's in the denominator. So we're going to take these 3 away from these 4 down here. And that's actually going to leave 1 x in the denominator. So this last problem, or term here, turns into a 3 over x to the 1st. And this here would be your final simplified expression after dividing those. And that's all there is to dividing by a monomial. Dividing by a binomial is just a little bit harder. And in order to divide by a binomial, we're going to take a little flashback to something you might have learned in about 4th or 5th grade. And in 4th or 5th grade, you probably learned something called long division. And you might have divided something like 24 and 5,406. And when you divided something like this, you actually had to pay attention to this entire 2-digit number, and you'd have to look at 2 things in here in order to figure out what to do, which is actually harder than what we're going to do with the polynomials, because you won't have to worry about both terms out here. But let's take a look at this. You looked at 24, and you went in 2 digits here, and you said, how many times does 24 go into 54? And you'd say 2. So you'd write a 2 up here, and then you actually did distribution. You just didn't realize it. You did 2 times 4, which was 8, to get an 8 here in order to figure out what 2 times 24 was. And then you'd do 2 times 2, which was 4, and you'd write a 4 here. And then you drew a line and you subtracted. And 54 minus 48 was 6. And then you carried down the next digit, which is a 0 here. Then you asked yourself, okay, how many times does 24 go into 60? And it goes 2 times again. So you'd write a 2 up here and do 2 times 4 to get 8, and 2 times 2 to get 4, and draw a line and subtract. And this time you get 12 for an answer. And then you carry down the next item for 6 here. Then you said, okay, how many times does 24 go into 126? And you'd say, oh, I think it's 5. So you'd go ahead and write a 5 up here. And then you distribute to figure out if 5 works and do 5 times 4, which is 20. And you'd put a 0 there and carry the 2. We won't have to worry about any carrying with the polynomials. And then 5 times 2 is 10, plus the 2 is 12. Then you draw a line and subtract and find out, hey, 5 worked, and I have a 6 for your remainder. And then you might have put a big R, 6, when you first started out. We aren't going to use a big R, we'll use a comma, or we'll write our answer in a similar fashion to what you did when you might have had something like 5,406 over 24, and you rewrote it as a mixed number. When you rewrote it as a mixed number, you'd do 225, and then you'd write the remainder over what you were dividing by, which I'm out of a little room here, so I'll rewrite it. and that'll be 225 and 6 over 24. So this eventually was how you rewrote it when you did mixed numbers, and this is how you started out. Instead of the big R, we're going to put a comma here if we write it in this fashion. If you write it in this fashion, we'll put a plus here between what's written here and there. And our problems won't just have numbers in them, they're going to have letters in them also. Let's take a look at how we're going to use the process we just reviewed for dividing by a binomial. Let's say that you have something that looks like 2x minus 3x cubed plus 4, and it's being divided by x plus 2. This is a polynomial, specifically a trinomial that you see here, divided by a binomial. Now, this looks like a trinomial. We're actually going to need something with 4 terms in order to do this division. And I'll show you why in just a second. When you're doing something that's being divided by a binomial, you want to rewrite it as long division. So we're going to put our division symbol, and we're going to put what we're dividing by out front here. And then we're going to put what we're dividing into, which is this, underneath our symbol here. But there's something specific about it. What's under here has to be in descending order. And it has to account for every single term going in descending order. So in descending order, I actually have to start with my negative 3x cubed. But then I need an x squared, and notice that this polynomial does not have an x squared. So what we're going to do is we're going to do plus, and then you can either just leave a space where the x squareds would be. If you don't do that, you'll run out of room when you're doing your problem. Or you can write in 0x squared, so that you can see that you are going down in descending order from 3 to 2, and then the next would be an exponent of a 1, which is this 2x here. And then finally on the end will be your constant of 4. So notice that this here is in descending order, going from a 3 to a 2 to a 1 to a 0 for your exponents. That is something that is extremely important. If you don't do that, everything will end up being all messed up, and you'll wonder what's happening. So now we have this in descending order. We've set up our long division. What do we do next? Well, with numbers, you cared about this entire 2-digit number out here and how far it went into all of this. With polynomials, you don't have to worry about that. You just care about this x and whatever's first right here. And you want to figure out what would I multiply this by to turn it into this. Now to do that, off to the side, you can actually do the division of that first term, which in this case is negative 3x cubed, divided by the first term of what you're dividing by, which is x here. This gives us negative 3x squared for an answer, which is what I'm going to put up here. And I always want to put it above my like term, which is above this 0x squared, since it has an x squared. So I'm going to put a negative 3x squared here. And I will color code this as long as we go down. That might be helpful for you, so colored pencils while you're doing these types of problems may be helpful. So now, negative 3x squared, we need to distribute to what's out here. So I'm going to start with negative 3x squared times x, which is negative 3x cubed. And then I'm going to do negative 3x squared times 2, which is a negative 6x squared. Then I'm going to draw my line, and we're going to subtract, but since we're subtracting this entire thing, we need to put parentheses around it. And then we need to remind ourselves, back when we subtracted polynomials, the subtraction sign actually distributed through the parentheses of what was after it. So this actually needs to distribute through here, and then we can just add straight down. So next we're going to change our color, change this to a plus, and change the signs of everything inside that parentheses. And then when you add straight down, notice these cancel. That's actually your goal every time, is to make sure those first terms disappear, and that's what happened. And then 0x squared plus 6x squared is 6x squared. And finally, we'll bring down the next term of a positive 2x. Now we just repeat the process all over again. Our goal now is to figure out what do I multiply this x by to get the 6x squared. So off to the side over here, I can do the same thing I did here, but with my new term. So I'll have 6x squared over x, and that's 6x. So that's my next item, and since it's positive, I'll do plus 6x. Now distribute it to the front. 6x times x is 6x squared. And then 6x times 2 is 12x. Draw your line, parentheses, and subtract. Now, just like in the last step up here, we had to distribute our subtraction. I'm going to distribute my subtraction here. And I'm going to change colors so you can see that happen. I'm going to go plus, and since this is a positive 6x squared, I'll change it to a negative. Since this is a positive 12x, I'll change it to a negative. Now when I add, notice the 6x squareds cancel. That was my goal. And 2x plus a negative 12x is negative 10x. And finally carry down the 4. Now my new goal is to make it so this 10x disappears. So I need to find out what do I multiply x by to get 10x. Again, we can do the division over here off to the side, and it's a negative 10. So I'm going to put a minus 10 up here. Distribute that 10 to the front. Negative 10 times x is negative 10x. And then negative 10 times 2 is negative 20. Draw your line, parentheses, subtract. And again, we need to change our color and then distribute our subtraction, which will make this negative 10x positive and the negative 20 positive. Those cancel, and 24 is our remainder because there's nothing else to carry down. Now, we can write this answer one of two ways. I could do a comma, 24 to signify the remainder is 24. Or, another way, which is a little bit better, is since the 24 is positive, I could put plus 24 over what I divided by, which is x plus 2. This here is your answer to this particular problem. Every single time you do these particular problems, you will follow the same process. And I have this process in detail on the written lecture notes also for you, so you could refer back to those every time you're doing a problem like this, or just review this video again. So you're now ready to do all your problems that deal with dividing polynomials. And your problems that deal with all of your exponent rules.